Good morning, good afternoon, good evening, class. This is Mr. Arosena, and today we're going to talk about derivatives of trig functions. This continues our study of derivative rules, where in 3.1 we talked about power rule and exponential functions, and in 3.2 we talked about product rule and quotient rule. Today we're going to talk about trig functions. And we'll get started with two of the primary trig functions, sine and cosine. Now, to help us visualize the derivative, or to calculate the derivative of this, we're going to look at a graph. And it's easy to visualize the derivative of sine if we look at a graph of it. Alright, so here I've already prepared the graph. Here is the blue is this graph of sine, and this black line is the tangent line at various points on this graph. Okay. Alright. And we're going to use the slope of the tangent line to help us sort of visualize kind of what's going on with the derivative. Because remember, derivative is really just a slope of a line. Okay, so let's start. Here with sine, at sine equals, or x equals 0 for sine, it looks like my slope looks to be approximately 1. Might not be exactly 1, but that's no fault of this graphing program. So at around 0, it looks to be about 1. As we move further down the sine curve, at pi over 2, so about pi over 2 here, the tangent line looks to be about 0. And let's keep going. As we get closer and closer to pi, it looks like our graph is, or the slope of this tangent line is looking to be about 1. Okay. And we'll continue on at 3 pi over 2. It looks like our slope looks to be about 0. And then at 2 pi, it looks to be about 1 again. Okay. That's really neat. It's really neat. Okay, and of course, it being sine, it's kind of periodic. It does this every 2 pi-ish. Yeah, whatever the period of the sine function happens to be. Alright, now, what other function is periodic? Well, cosine is. And there's a cosine graph. Now, let's take a look at something that's really neat. Okay, so as I move this here, so here at x, or at x equals 0, we said that the slope of this tangent line is approximately 1. And let's take a look at the cosine function. Look at that. The value of the cosine function, that's this number here, also happens to be 1. Now let's move this tangent line further along. So let's say the tangent line at this point, again pi over 2, looks to be about 0. And if I go cosine of pi over 2, the value of cosine of pi over 2 happens to be, well, take a look, it happens to be 0. Okay, let's keep going. At pi, about pi, you have a tangent line of about 1, and it looks like, or negative 1, sorry, this is a negative slope. The cosine also has a value of negative 1. Let's keep going. Does this pattern continue? There, at about 3 pi over 2, slope of 0, cosine, lo and behold, is also 0. And finally, let's complete the circle, or complete the rotation at 2 pi, slope of about 1, and cosine value is 1, as we would expect. Okay. Now, without going into any kind of like crazy mathematical proof, like the actual rigorous proof, it looks to be that if I take the derivative d of dx of sine x, it looks like the derivative is going to be cosine of x. Okay, based on the visualization of our graph. Now, what about cosine? If I look at cosine, so I'll leave the same graphs there. Here's cosine. Here's cosine. And cosine kind of similar. Like there, at x equals 0, the cosine graph has a graph of, where its tangent line slope is about 0. About 0 at x equals 0. My tangent line has a slope of 0. And it turns out that the value of the sine happens to be 0 at x equals 0. Interesting. Let's go on to pi over 2. At about pi over 2, so it's about here, give or take. The slope of the cosine function at that point, that looks to be about -1. But wait. The sine value is +1, so it's not quite the same. But it only differs by a factor of -1. We could probably work with that. As I continue on, at pi, cosine, the slope of the tangent line looks to be horizontal, so it's about 0, or is 0. And the sine function ends up being also equal to 0. Continue moving, that's 3 pi over 2, it's about there. Cosine, the tangent line has a slope of about 1, but unfortunately the sine value is -1. Wait, over here, the sine value was 1, but the slope of the tangent line of the cosine function was -1. And over here, the slope is +1 on the cosine, but the value of the sine is -1. Like, it looks almost like a negative relationship. At 2 pi, sine is 0, and I guess this pattern continues. There, cosine slope is -1, sine value is +1. So it turns out that the derivative of cosine is really just the negative of the sine value at that point. Okay? Then these two are actually correct. Without going, there are actual more rigorous mathematical proofs out there, and you can prove it for all values of x. But for now, for our purposes, the visualization that we just saw will suffice to show us that the derivative of sine is equal to cosine, and the derivative of cosine is equal to -sine. Okay, and that is our derivative of sine and cosine. Okay. And again, I'll have a link for a more rigorous proof in the description, so you can see somebody else prove it for all values of x. Okay. Now, with these two definitions, we can actually move on, and we can calculate the derivative of tangent, because if you recall, tangent is really just sine over cosine, and we learned quotient rule earlier, so we can just use the quotient rule again to calculate the derivative of tangent. Okay. So, armed with this knowledge, we can now calculate the derivative of tangent, which I'm going to write tangent as sine x over cos x, because remember, tangent really is just that. And using our knowledge of quotient rule, we can say the following. This is really g times f prime minus f times g prime, all divided by g squared. Alright, so in this case, g is cosine, so this will be cosine times f prime, or f is sine, so derivative of sine we just saw was just cosine. Let's just put the x's in for completion's sake. Okay, minus f, this is going to be sine x, and then g prime, well, derivative of cosine is negative sine x. And this will all be over cosine squared x. Alright, let's simplify a few things. This is going to be cosine squared x. Negative sine times negative sine is positive sine squared x, all divided by cosine squared x. And if you hopefully remember this from previous math classes, this cosine squared, so this here, cosine squared plus sine squared is really just equal to 1. So this becomes 1 over cosine squared x, which is really just secant squared x. Right. And there you go. There's our derivative of tangent. So d by dx of tangent x is really just secant squared x, as shown by combining the derivatives of sine and cosine with quotient rule. There you go. Now we have the derivatives of all three primary trig functions, or trig ratios. Okay. You can prove the other trig ratios. Okay, you can prove the other trig ratios using quotient rule, and I'll leave that as an exercise in your assignment. But you can use the quotient rule to find the derivatives of the other reciprocal trig functions. As a reminder, the other trig functions are secant x, which is 1 over cosecant x, which is 1 over sine, and cotangent x, which is 1 over tangent. Although I prefer to write it as cosine x over sine x. Okay, so those are the reciprocal trig functions. And I'll leave it as part of your assignment to calculate the derivatives of the reciprocal trig functions, secant, cosecant, and cotangent. Right, let's go through a couple examples. So, real quick examples to help you get used to using the derivatives. Let's differentiate the following. Okay, so here we go. F of x is equal to x cubed times cosine x. So this is two functions being multiplied together. So f prime is, well, let's see, f prime will be, I shouldn't write f prime. I'll write it as f times g prime. So the derivative of f times g, because we really have two functions, f and g, is going to be f times g prime plus g times f prime. Alright, so first function is x cubed. So this will be x cubed. G is cos x, so find the derivative of cos x. Derivative of cos x is just negative sine x. Alright, plus cosine x, and then derivative of f is going to be 3x squared. And there we go. There's the derivative. We can simplify it a little bit if you really wanted to, just to clean things up. So this would be 3x squared cos x minus x cubed sine x. Doesn't really change much, just looks a little neater. But there you go. There's our derivative. This is our derivative. Alright, simple enough example. Let's go through another one. Oops, I'm going to erase some ink. Okay, here, let's find the derivative of secant x over 1 plus tan x. And let's call this f, and we'll call this g. Okay, so we have two functions, f and g, and we're going f divided by g. So we can basically say the following. The derivative of f over g prime is equal to g times f prime minus f times g prime divided by g squared. Now, we don't actually know what the derivative of secant is, but I'll give it to you guys here. Whoops, got it wrong. d by dx of secant x is equal to secant x times tan x. Okay, this you can prove again. This is going to be part of your assignment to prove this. Well, if you choose to do that question, is to prove that derivative of secant is secant x times tan x. It is, by the way, it is. You can find it in any table of derivatives. Alright, so now we have that knowledge, we can continue on our application of the quotient rule to this. So secant x, so g times f prime, so g is 1 plus tan x. F prime, well, f is secant x, here's f prime. We secant x tan x minus f, which will be secant x, times g prime, so that's derivative of this. Derivative of this is going to be 1. Derivative of 1 is 0, so don't have to worry about it. And derivative of tan x, which we said earlier was just secant squared x. And this is all divided by 1 plus tan x, all squared. Okay, we can sort of clean this up a little bit. So we would get the following. I can factor out a secant from everything. So I can take out a secant x. This will leave me here with 1 plus tan x, I guess this will be multiplied by tan x minus secant squared x, all divided by 1 plus tan x all squared. Okay. And I guess we can leave it as is for now. There's really no reason to do anything else to it. We can just leave it like this. We probably could simplify it a little bit more, but that's just an exercise in algebra, which we don't really need to do. Alright, and there you have it. There's the definitions for the primary trig functions. We can use those definitions in combination with product and quotient rule to help you find the derivatives of the reciprocal trig functions. And then it's just a matter of applying it with all the various questions you may encounter in this section. Alright, that does it then for this. I think we've discussed enough rules, and then if you have any questions with your assignment, come see me in class.